So, welcome to module 2 lecture 1. So, in module 1 what we have generally discussed. So, we have seen that there is a digital VLSI design flow, how it works, and then we have seen that we require CAD tools or automated tools which can automate the design flow, because I mean it's a digital designs. If you start from specification, then you have to go to the final product design. It involves lot of steps like high level synthesis, gate level synthesis, layout, and then final test pattern generation and so forth, which are extremely complex and cannot be done by a human being on by manual procedure. So, we require automatic algorithms to solve all the problems for us. And then we have told that in the from the next module onwards, that is from module 2 onwards, we will be looking into CAD tools or algorithms, how we can develop good algorithms which can enable a designer to take help of those CAD tools and he can get a very smooth and automated design flow. So, that is the basic goal of this course, for that we will be learning about digital design flow, verification flow and test flow, and how we can develop CAD tools which can help us automate this flow. So, that is the very basic emphasis of the course. Then we have seen that for any procedure or any algorithm you have, so if you want to process some data from the algorithm, so data should be represented in a a formal manner by using some formal model, so that it can be easily transformed and it can be easily processed. Then we have seen that control and data flow graphs are very important. I mean are very important parts. I mean these are very important actually data structure, or you can say a model which can represent our design specifications. We represent in hardware definition languages, and then we can very easily represent them as control and data flow graphs, which can be processed by all the algorithms or all the CAD tools which we will see down the line, so that you can get an automated design flow. So, in this course in this lecture, I mean module 2 first lecture, what we are going to see, we are or in other words say, I mean module 2 will be basically dealing with high level synthesis, that is we will be taking a CDFG or a Verilog code in the beginning, and in the end of the flow we will generate what? We will generate a architectural design for this for this specification. So, this is actually called the high level design flow. So, the high level design flow, as we will see, will consist of three problems: scheduling, allocation and binding. So, we will be looking at algorithms which can automate this three problems. So, in the first lecture we will introduce the problem of high level synthesis, that comprises three parts: scheduling, allocation and binding. So, first we will see the problem, and then from lecture second, third, fourth onwards in this module we will see how we can design CAD tools which can automate this process. So, we saw in the last lecture that first step is to obtain for VLSI design we have to design VLSI design, we start with the specification, and the first step we obtain is a RTL level circuit. So, what is the idea? So, we write a specification in Verilog or VHDL, so that because it is unambiguous, and if you write it in English language, so it may have ambiguity and all. So, we generally prefer to write the specification in Verilog or VHDL kind of a HDL hardware definition languages, and high level synthesis will transform it to what you call a RTL circuit or a architectural block level diagram. Okay, so, to obtain this from specification to RTL, we require high level synthesis algorithm. So, high level synthesis basically transforms your specifications to an RTL, and specifications, as we have already seen, are generally represented in terms of some kind of a control and data flow graphs. So, CDFG is one of the most widely accepted tools for this, and then what we will do is that we will take a CDFG and we will convert it into RTL level circuit or block level architecture. So, we have to, so high level synthesis actually takes as input the optimized CDFG and perform scheduling, allocation and binding. So, why do you talk about optimized CDFG? Because in the last lecture of, that is the third lecture of the first module. So, what we have seen that sometimes I mean the RTL designs, or actually the what you call the Verilog designs or specifications in terms of Verilog designs are generally written by human beings. So, you express your specification, which is a manual activity. So, from the designer's experience, he looks at the specification and then he writes a Verilog code or a hardware code, hardware definition language code, so which can satisfy the specifications. Now, we have seen that as a human procedure, so it may have lot of inconsistency, it may have redundant codes, like it may have dead codes, it may have loop invariant computation and so forth. So, if we can do a pre-processing, like we have seen compiler compiler based optimization, then we have seen graph based optimization, then we have seen the last level like what you call the technology library, that is fabrication library or tech library based optimization. So, several optimizations, or where we have reduced the eliminated redundant codes, or we have made our design more optimized by using an incrementer instead of an adder and so forth. So, all these optimization steps we have already seen in the last lecture. So, they are applied actually to the main specification, so that we get a very optimized specification in terms of hardware, power, area and frequency. So, that is actually sometimes called a pre-processing step. So, we take a CDFG which comes as the input from the specification, then we go for the pre-processing step, that we optimize it, and then we go for scheduling, allocation and binding problem, which generates the RTL design, or in other words which is your architectural level block level design. So, that is the idea of high level synthesis. So, high level synthesis will take your pre-process design. So, pre-process means we have already done the optimization on the CDFGs or on the HDL codes, and finally the CDFG or your input will be scheduled, allocated and binded, and finally we get a RTL level or we get a block level design. So, that is the basic idea of high level synthesis. So, in this lecture we will first see what is scheduling, allocation and binding problem. Then in the next lecture onwards we will see how we can develop an automated CAD tool which can solve the problem. Okay, so in other words we are now looking at the high level design flow. So, the whole broad level VLSI design flow already we have seen. We start with high level design, then we go for gate level synthesis, then we go for back end design, and and from back end design we go for fabrication, and also in meantime we also generate the test pattern, that is actually called the test flow. So, now we will go in depth in one of the flows one by another. So, first we are looking at the high level design flow. So, what we have? We have functional representations that we say what we want to do, like we want to add, we want to implement a multiplier, etc., etc. Then we go for an intermediate representation. So, what do you mean by intermediate representation? In this case it was a control and data flow graph. So, we are representing it in a manner so it is very easily usable by your automated CAD tools. Then actually here also sometimes we do a lot of pre-processing, as already we have seen, to get an optimized design, because functional specifications what we are writing basically are manual driven procedures. So, they are done manually. So, sometimes we require optimization. Then the first stage is that we go for scheduling. So, we will all see in details what the scheduling means. Scheduling means in case for each of the operations we give a time step, that this operation will be done or in this time step and so forth. Then whenever we have scheduled all the operations, then we actually allocate some hardware units for this. Like for some case we may require a hardware adders, or for some case we require a multiplier and so forth. And finally, we are actually allocating what you call the variables will be allocated to registers, then there will be multiplexers and so forth. So, first we go for scheduling, then we allocate it to the hardware, and then we bind the operations to the hardware, like say addition 1, addition 2 will be done by adder 1, addition 4 and 5 will be done by adder 3 and so forth. Okay, so and finally we go for control and data path generation, and that is we will see what you mean by control and data path, and finally we get the RTL design, or what do you call your block level architecture design. So, this is the basic flow, and now in today's class or today's lecture we look at all the problems in details in a more formal way. So, as I already told, the first step in high level compilation is an internal representation. So, it is a control and data flow graph. Then we go for pre-processing step. So, what do you mean by pre-processing step? That is, we go for some kind of optimization so that the code is more optimized, or it has do not have any redundancy, or it is more what do you call it, uses better hardware elements like incrementers or shifters rather than adders or dividers, multipliers kind of a stuff. So, we are using better, we are keeping the circuit very optimized, because we do not have any redundancies, we do not have any what you call dead codes, etc. And finally, we are using very good quality blocks. So, this type of optimizations we do it. So, that is actually called the pre-processing of the high level or your specification. Then what we do? Then we actually go for operation scheduling. So, as I already told you, what do you mean by operation scheduling? So, in a control and data flow graph we have some operation nodes. So, each of the operational nodes we should assign it to what? We should assign it to some time step, that is this operation will be done in time step 1, this will be done in time step 2 and so forth. So, that is actually called operation scheduling or scheduling in a high level synthesis terminology. We will see the details the actual formulation of the problem. Then this is actually the second step. The third step is called allocation. So, that is what you mean by allocation. Now, we have an adder. So, we say that this is the adder, how you want to implement the adder. So, you can use it use a hardware adder like multiple carry adder. Also, you can use a carry look ahead adder or carry save ahead adder. So, in the allocation step, for each of the operational nodes or each of the operators like adder, multiplier, subtractor, we allocate a hardware block, and we can also say that in this step we actually physically look at the design library, what are the components available there, or what are the adder, multipliers, divider, subtractor available there, and we try to allocate them to each of the operational nodes in the CDFG, or in the scheduled CDFG is a better way to say. Then in the fourth step is actually called the binding. Now, say we have taken 3 adders only and 2 multipliers only, but there may be 10 additions which can be done. So, obviously, all the additions cannot be done in one step. We all see that, because sometimes it may not be possible, even if there are 10 additions that are required to be done in the CDFG, you cannot do it in one step. So, we put only 3 or 4 adders maybe, and we try to reuse the adders. Now, reusing the adders means we can say that operation 1, 2, 3 or addition 1, 2, 3 will be done by adder 1, and addition 3, 4, 5 will be done by adder 2 kind of a thing. So, this is actually called binding. So, in binding what happens, each each of the operations which are already scheduled and allocated. So, if you will actually bind it or physically assign it to one of the hardware which has been taken in the case of allocation step. In allocation step we take some hardware adders, multipliers, subtractor, whatever from the library, and in binding step we say that operation 1 will go to this hardware, operation 2 will go to this hardware, and so forth. Okay, and also we take care of registers to store the variables, etc. All these things are done in case of binding. And finally, we go for data path and control path generation. Now, we will see, I mean, what do you mean by control, because if you say that adder 1 will do operation 1 and operation 2. So, in case of operation, maybe A and B should be fed to the adder, in case of operation 2, C and D may be fed to adder, fed to this adder block. Okay, so we require a lot of multiplexing arrangement and all. So, depending on which time step you are or which of the two variables you want to add in the adder, so you may require to generate some control signals. So, in the final step we generate the control signal and the data paths. So, this is actually control, I mean this is in a nutshell is a high level synthesis flow. Now, what we will do, now we will take each of the problem in a more formal way, and with examples we will try to explain what do you mean. Okay. So, then it will be, now the definitions may be a bit fuzzy to you, but that is actually we are telling it in a very layman kind of a language. Now, we will come to a in very depth level, or what you can say we are coming to a more technical level of doing it. Okay. So, now what is the scheduling problem? So, I already said that in a CDFG we have some operations. So, this procedure what it will do, it will try to allocate a time step to each of the operations. So, what it says that let O be the set of operations which are to be scheduled. So, set of operations you can easily get from the CDFG, and each individual operation we say that OJ belongs to O. So, now what you in high level scheduling problem, what you do, you will take each operation from the set of operations, say OI is an operation which belongs to capital O. So, each of them has to be given a time step. So, you can say that this happens in time step 1, this should happen in time step 2 and so forth. But one thing you should be very careful in doing that, if there is an operation OJ which depends on the result of OI. So, it may happen that output of OI is actually controlling output of OJ. So, in this case you should be very much assertive that this has already been scheduled before the second guy is scheduled. Why? Because the output of this the output of OJ depends on the output of OI. So, OI has to be computed first, then you can compute OJ. So, it is very obvious that you have to give a prior time step to OI compared to OJ. Then you can you can easily do this. So, this is actually called data dependency. So, if the output of OI actually controls the output of OJ, or OJ is dependent on the output of OI, so there is a data dependency. So, when you are scheduling it, you should take very much care that you or it is a mandatory requirement that this partial order, or what do you call this, dependency is satisfied. Otherwise, obvious, it is very obvious that if some OJ depends on OI and OI is not yet scheduled, then if you try to schedule OJ before OI, so you may get inconsistent result, right. So, that is the very basic idea. So, that is actually data dependency, and that has to be very much taken care, or the mandatory requirement in case of scheduling. Okay. So, let us now see that there are different types of scheduling problems. So, we will see one by one. So, one is called the unconstrained scheduling problem. So, there is no constraint. So, there is only one constraint, actually we should not call it unconstrained, there is only one constraint, that is data dependency has to be managed. Otherwise, there is no constraint like you have to complete all the operation in force time step, there is no requirement that you require so many adders, so many substructures, there is no resource constraint, there is no timing constraint, etc. So, this is called the unconstrained scheduling, but of course, you have to follow the dependency. The second thing is called actually time constraint scheduling. So, what does it say? It says that you will give a time constraint that you have to go for the scheduling should be possible in 3 time steps or 4 time steps. So, sometimes you may get a successful result saying that yes, it is possible, and sometimes you may say that it is not at all possible. Why it is not at all possible? Because you may say that we have given a constraint of 3 time steps and it is not doable in 3 time steps. Then there is a resource constraint time scheduling, in which case time is not a matter, but we will tell you that we will give only one adder, only one multiplier, only one subtractor kind of a thing, and you have to reuse them again and again, and you have to get the solution, or you have to get a scheduling, you have to schedule all the operations. Okay. So, it may happen that you will take a very long time to do it, because there may be a constraint on the resources, and sometimes the resource constraints also may be something like that you may not be able to solve your problem. Like for example, it may happen that you require a there is a subtraction operation and you said I do not have a subtractor, then obviously it is an infeasible schedule problem and you cannot schedule the CDFG at all. And finally, we have time and resource constraint scheduling problem, in which case both of the problems are together, that is you have a definite time constraint as well as you have a definite resource constraint. So, this is a very most practical time scheduling problem. In most of the cases we use resource and time constraint scheduling problems, because we say that I have to do all the operations in so and so many time steps, as well as I have this is the maximum number of resources, you cannot have anything more than that. Now, you can understand that sometimes our constraint may be too tight and you may lead to an inconsistent solution, then you have to relax one of the criteria, like you may say that I have to extend my time step, or I have to put more hardware to get my solution. But in all of them you have to understand that one constraint always remains, that is the data dependency. You cannot anyway violate the data dependency. Okay. So, that is the idea. So, we will now elaborate all the examples, I mean all the problems using this expression A plus B plus C plus D star E. So, this is the basic expression we will try to do. So, unconstrained scheduling problem. So, what it says that we have a set of operations O. So, O1, O2, O3, O4, these are the set of operations, and T is the set of different type of functional modules available. So, in this case say we can say that T1 stands for adder and T2 stands for multiplier, say, okay, and T1 belongs to capital T and also T2 belongs to capital T. This you have to know. So, okay, so these means O1, small O1, small 2, O2 and O3 are the operations. So, all they belong to capital O, and T is the set of different types of functional modules. So, this is the idea. So, we have T1 and T2, only 2 types are required. So, they belong to capital T, and you have to define a function Ty. Actually, what it does is maps O to T, that is it maps each of the operations, okay, each of the operations to a hardware module, okay, and a partial order as the constraints. Okay. So, let me tell you what is the idea. So, to solve it, what we are given? So, we are given O, that is the set of operations. In this case 1, 2, 3, 4 are the operations, and the different types of functional units available. So, in this case T1 and T2 are available or required because it is multiplication addition only, and a partial order on O is also given. So, what is the partial order? Partial order in this case you can see that without computing O1 and O2 you cannot go for O3. So, that is what there is a data dependency, that you have to compute these two first, then you can go for this. But O1 and O2 do not have any data dependency, you can do any one before other or after the other, there is no dependency on this, but you cannot compute O4 before O3. Similarly, you cannot compute O3 before O1 and O2. So, this is the partial order or the data dependency. Now, what you have to go for this unconstant time scheduling says that a feasible schedule schedules you have to schedule all the elements in O, taking the appropriate modules from T, that is you have to schedule O1, O2, O3, O4, that is you have to give it some time steps to this, and also you have to say that for O1 I allocate T1, for O2 I allocate T1, and like for O4 I allocate T2 because T2 is a multiplier and all others are adder, and you should obey the partial order, that is data dependency, data dependency has to be followed. But now it is an unconstrained time scheduling problem. So, the unconstrained problem, so what is the idea? We do not have any requirement that how many adders we can give, how many multipliers we can give, or what are the time steps, we do not at all bothered. So, this can be very well unconstant time schedule which is given. It says that in O1 I will allocate T1, O2 I will allocate T2, O3 I will allocate T1 because they are all adders, and O4 I will allocate T2, right, the multiplier, and O1 and O2 I will do in time step 1, O3 I will do in time step 2, and O4 I will do in time step 3. So, I have given all the operations some type of hardware, as well as I have given time steps, as well I have said that as well as I have taken care of the data dependency, that is the partial order data dependency I have satisfied. So, this is a schedule, unconstrained schedule, because I have not thought that what would be the time limit maximum or what is the number of adders required. I do not think, but I give a feasible schedule for this one. So, this is, you can say that unconstrained schedule for this expression. Now, how many adders, multipliers, subtractors you require if you think? So, you can see that I require 2 adders because they are happening in parallel in one time step. Now, in time step 2 you can either reuse this or you can reuse this, and then we require 1 multiplier. So, resources required are 2 adders and 1 multiplier. Okay. So, so whatever I discussed actually is written over in this slide, that is 3 additions, the O1 and O2 and 1 multiplication, this thing. So, we use T1 is the adders. So, O1 and O2, O3 are all assigned to T1, O4 is assigned to T2, and then actually we define the time steps, that O1, O2 in time step 1, O2, O3 in time step 2 and O4 in time step 4. So, that is what has been done. So, we require 3 control steps and we require 2 adders and 1 multiplier module for this one. So, this is an unconstrained time schedule. Now, we go for a time constraint. So, in this case we should give some time constraint, that you should say that we have to do all these things, like O will be given, T will be given, a function will be given, that is actually you have to say that this type of, like for adders you have to apply to addition operations, you have to apply to adders, the multiplication operation you have to multipliers and so forth, that is for So, in terms of operations and different type of functional modules, type function, all these things are given. Along with that, all these things are available in unconstant time scheduling problem also, but in addition of that, we are also given a deadline, that you have to say that we have to do everything in so many number of time steps. We are not allowing more than say 3 time step or more than 4 time steps, not allowed. So, you are giving a deadline, and everywhere this partial order is there because you cannot obviously violate your timing constraints. Okay. So, so now what you have to do, you have to find out a feasible schedule okay, for all the elements taking appropriate modules from T, meeting the deadline. This is a new constraint that is added because of time and obeying the partial order. So, that is what you have to do. So, in the last example, if you look at it, so in this case the time constraint is, if you say that my time constraint was 3, so this unconstrained scheduling problem was can be converted into a time constraint 3 time constraint free scheduling problem, because here we are able to do it everything in 3 time steps. Okay. Now, let us see. So, let us define. So, in last example you can say that it was an example of a time constraint scheduling when your time requirement or deadline was 3. Okay. So, what is the resource? So, in this case one more thing you have to observe. So, like in this example, so this is a scheduling problem with time constraint 3, those is satisfied. So, if I tell you that I want similar schedule to be done, but my time constraint is 2. So, you will find out that I will land into an inconsistency, because you cannot do everything in 2 time steps, because at least for the you cannot compute this in parallel with this one, because the results of T1 and T2 O1 and O2 are required to get the value of O3. So, you cannot put this guy here, it is not possible. So, you require at least one step for this 2, one step for this one, and similarly this one also you cannot put parallel over here, because the result of O3 is dependent, O3 controls the result of O4. So, you require minimum 3 time steps to solve the problem. So, if you say that I want to solve a time constraint scheduling problem with time step 2, so you will not be able to do it. So, if you say it is 3 or more, then you will be able to solve the problem. Okay. So, this was about your time constraint schedule problem. Now, we go for the resource constraint scheduling problem. So, resource constraint time scheduling problem is very similar. You have O, T, and then the function, it maps all the the operations to different type of hardwares, and along with that you have a resource constraint. So, what is the resource constraint says? It says that K is a type of operator, like it adder, it can be multiplier, it can be subtractor, and it has a limit. It says that it is 1 to max of T. Okay, that is what. So, it says that you can have say I will use maximum 2 multipliers. So, K is the type. Okay. So, like in this case you see for each functional type of Tk, you can have a function like this. Oh, sorry, you can have an inequality like this. It says that it says that Tk, say you can say that equal to 1. So, that means for the particular type of hardware operator, like in this, if say we can say that T1 may be adder in this case. So, we can say that T1 is equal to max of T1, say 2. So, it says that maximum you can have 2 adders in your circuit. So, if I say that T1 equal to 3, so you can say that maximum 3 adders can be possible. So, like T2 stands for a multiplier. So, you can say that T2 equal to 1. So, it says that maximum you can have only 1 multiplier in this one. And so, how many, so what is the limit? So, minimum should be 1. So, if you do not have any hardware, any multiplier, no problem can be solved. So, it says that Tk is actually a constraint. It says that what is the maximum number of operators available, or maximum number of hardware, each hardware type that is possible. So, So, it starts from 1 to max of T. So, that so T is the maximum number available. So, you have to specify that along with the number of operations, different type of hardware elements, partial order, and also you have to tell what is the maximum number of elements per hardware type you are having, you want to put it. That is one time resource constraint. So, you are putting a resource constraint there, and then you have to perform a feasible schedule for all the operators, for all the modules in T, as well as you have to meet the resource constraint here. Okay. So, in the last case we were talking about the time constraint, now we are having a resource constraint. Now, let us assume the case resource constraint where I say that maximum T1 is equal to 1 and T2 is equal to 1. So, you can have a maximum 1 adder and maximum 2 adder. Time constraint is not there. So, that means what? You can have you can do parallelly 1 addition at a time. So, a feasible schedule is this is one T1, this is one T1, and this is one T1. So, what we do in first step we go for operation O1, then the same adder we use for operation T2, then the same adder we use operation T3, and finally the multiplier for T4. Now, you can see that this is a feasible schedule, because now O1 has been given T1, O2 T time step 2, O3 time step 3, and O4 time step 4. So, now you require 4 time step, because now the constraint is not 2 adder, but the constraint is a single adder. So, you have increase in your time step. So, if you remember last example, so if our constraint was set adder is 2, then we could have shifted this guy over here, then this thing will be shifted here and this thing will be shifted here, and then your time constraint requirement will be at 3. So, now because you have given a severe resource constraint, so your time your time step have increased. Okay, now resource constraint time scheduling problem, that is what I have discussed. So, in this case the number of control step is 3, and because in the last example it was in time step 3 because of the time constraint. So, what I have discussed is written in the slide. So, I mean because of the time resource constraint, so you have increased your time step. So, now if you say that I want to have a resource constraint of 1 and a 1 and till I want to get a schedule in 3 time steps. So, this is the infeasible requirement. So, you have to either increase your time steps or you have to increase your hardware requirement. So, that is the next definition, that is called time resource constraint schedule. So, in this case it was only about the time, only about the resource constraint. So, he is saying that or the designer is saying that t equal to 1 and t equal to 2, that is maximum 1 adder and maximum 1 multiplier. So, you require 4 steps. Okay, so, it is one more than the case when your requirement, when the constraint may be 2, that is 2 adders kind of a thing. Okay, so, we have increased from 3 to 4. Now, in what is the next problem, resource scheduling problem we have seen, that is both resource as well as time both may be constrained. So, if somebody says that T1 equal to 1 and T2 equal to 1 and time is equal to 3. So, you can say that it is impossible to generate, or it is an infeasible situation to generate a schedule in this way. So, you may have to either say that I have to either increase my time resource requirements to say 2, and then you can follow this, or you have to say that even if I want to keep my resource constraint less or severe, that is 1 1 1. So, you have to go for a time constraint of 4. Okay, so, this is how sometimes we lead to inconsistent schedules, and then you have to go for a better schedule. We have to restrict one of the, we may have to relax one of the requirements, and then we can give you a successful schedule. So, what we are learning over now, so what we are seeing is that we are looking at the schedule problems. We are not giving you the solution, that given a constraint how you get this graph. Okay, given 1 1 and 3 how do you get this graph, or given 1 1 and 2 we said this is not possible. So, how automatically we can get it, that we are not discussing, that we will be discussing in the following lectures. In this lecture what we are doing, we are just defining you the problem, what are the problems, and algorithms will be looking in the in the next lecture onwards. So, now you don't think about how you can automatically do that, just try to understand the problem. So, in time resource constraint scheduling problem is O set will be here, T set will be there, there is set of operation, different type of elements, this function is there which maps the operation to the type of hardware, then there is a resource constraint as well as a deadline constraint. So, we are slowly increasing the number of constraints, as well as there is also a what you call the data dependency, that has to be also, there is partial order you have to always follow. Then you have to go for a give me a proper schedule, and then you have to say that the proper schedule matches both this what do you call this resource constraints as well as the time constraint. Obviously, you have to follow the partial order of data dependency. If you follow everything, then it is a feasible schedule, but if one of the, say that one of the parameters is not being met, like for meeting the time schedule you are not able to meet the resource constraint, and then for missing the resource constraint you are not able to meet the time constraint, then you said infeasible, then you have to relax any one of them. Okay. So, that was about the scheduling problem. Now, assume that this scheduling has been done. So, that is all the operations have been given some time step. Now, what you have to do? So, now you have to find out exactly, now in this case if you remember, we are saying that you require a adder. This is T1, you require a adder, here you require a multiplier. So, this is actually, we are just, it is just a name that you are using a adder, you are using a multiplier, and you are using a what you call a subtractor. But now we are not telling exact nature of the multiplier, exact nature of the adder or something. Like that, you know, that lot of adders are possible and they may be available in the library, like ripple carry adder, carry look ahead adder, carry save ahead adder. So, some adders are faster, some adders are slower. Faster adders are generally high in area, they take more power, we all know that. Slower adders are generally less area, they take less power, and so forth. So, in the step of allocation procedure, you have to look at the design library, and then you have to typically find out or exactly find out which is the type of adder or which exact hardware module you are going to be implement for each of the operations. Like in this case, you may see that there are two adders like T1 and T, these are two different addition operations. So, it may happen that you may take it to be a carry look ahead adder and it may be a ripple carry adder. Sorry, in this case they both are similarly used, we should not take this example. Like in this case we may think about this example. So, we may think that these are the two different adders, they are working in parallel, so you have to put two adders. So, you can think that this I will be taking as a ripple carry adder and this will be taking as a carry look adder. This is also possible, they are both adders, but you can take, they can be allocated a different what you can call different hardware, actual hardware element. So, allocation problems will take you taken the schedules which you already made. So, what you do, you take the exact hardware that is required and you put it. Okay, and like this today the design library will tell you what is the power requirement, what is the area requirement, what is the frequency, everything will be mentioned there. So, it will be very easy for you to select this one. Okay, select what type of adder or multipliers you require. So, let us take a typical example. So, let be this table be our design library. So, what we have two adders, one is at slow adder, one is a fast adder. I am not typically mentioning it is what is the type, like ripple carry or carry save. We are not saying that. We are saying that there is a slow adder, there is a fast adder, the type is T1, then subtype, we have to also mention the subtype. So, T1S is slow, T1F is fast, then we can say the frequency is F of T1S and F of T1 fast. So, this is the frequency of the fast adder and the slower respectively. Similarly, this is the area, this is the power, okay, and then we have two types of multipliers also, type is T2, subtype is T2 slow, T2 fast, and similarly here we have defined our frequency, area and this one. So, as a general rule of thumb is that generally if the elements are faster, so frequency will be higher, area will be higher and power will be higher. So, generally this relation will hold. So, what do you mean, what I am saying that? So, this is a slow adder, so frequency will be less, okay, sorry. So, fast adder, so this frequency will be higher, this frequency will be low. So, area of this fast adder will be also higher than the area of the slow adder. Similarly, power of the slow adder will be also less than the power taken by the fast adder. So, everywhere this one will be higher than this one. Similarly, in the case of multiplier. So, we see that always the slow frequency of the slow adder will be less than the frequency of the fast adder, and similarly the area of the fast adder will be higher, area of frequency power of the fast adder will be also higher, and similarly case of multiplier. Generally the hardware which is faster has more frequency. So, it is obvious this generally it will take more area and more power kind of a thing. So, the general rule of thumb. Okay, now we have to, now let us take this unconstrained problem. Okay, now what we have to do, let us take this one. So, this guy, and then we have to say that which is the exact adder. Now, it was T1, T2, T3, T4, sorry, T1 and T2 kind. Now, you have to say that which I will use. You have to say T1F or T1 slow and or T2F and T2 slow. Okay. So, now we will explain that later on with the slides, but now let us just see how we can do that. So, generally what happens, multipliers are very slow circuits, it is slow circuits because it is very complex, multipliers are complicated operation compared to adders. So, it is even happens that your frequency of T2 faster will be, that is the frequency of the fast multiplier will be also less than frequency of T1 slow. That is a very typical thing you have to understand. Again, I have to re-emphasize, multipliers are very complex circuits compared to adders. So, even if you take a very slow adder, in this case say T1S, so the frequency of T1S, that is the frequency of the slow adder will be still higher than the frequency of the fast multiplier. That is a very interesting thing to observe, that even if you take a very fast multiplier, still the frequency or the operating speed of your slow adder will be higher than that. So, that is a general rule of thumb we will take, and then we will try to go for the allocation procedure. So, you will know that these are the time steps, and that means it takes some frequency, or this time step has some time units. That means what? So, if you say that this is say 25 nanoseconds. So, what does that mean? That means that your these two additions they are operating in parallel, they should be over much before 25 nanoseconds. So, if you take it as 10 nanoseconds, then you may be in a problem, because then you say that step 1 or step 2 or step 3 of these steps are of equivalent size. We are assuming typically for the sake of simplicity. For complex examples or complex cases, the time steps may also vary in size. So, sometimes some cases we have 10, sometimes 20. They are uneven time steps, but there are for complex and multiple clock type design. So, we are not going into those complexity in this course, okay, because our idea in the course is to take an overview of the whole design flow rather than going into in depth in one of the areas. Okay. So, let us assume that all the time steps have equal length, equal time period. So, if you say that it is 10 nanoseconds and say if the addition here takes 20 nanoseconds, so you will have a problem, because even before the addition has been done, you will come to the next time step or the clock will arrive. So, that will be a problem. So, whenever we say that it is a 25 nanoseconds, something like that, then it should be able, you should assure that these two operations are done, these two operations are done, and this operation is also done. So, who will decide what is the time step length? So, it is very obvious, the slowest guy in the whole schedule process will determine that. So, if you say that these addition multipliers are very complex, they take a lot of time, so you can say that it takes 40 nanoseconds to do your solve the problem. So, obviously, everything will be 40 nanoseconds by default, because here you have to use 40 nanoseconds, because your multiplier is doing the solving your problem in or doing the multiplication in 40 nanoseconds. So, obviously, if you put 25 and adders are doing your job in 25 nanoseconds. So, instead of 40, if I put 25 nanoseconds, so these guys will not have a problem, these guys will not have a problem in generating the output, but if I put instead of 40, if I put 25 nanoseconds, then the adder multiplier will not be able to do its operation and will be in an inconsistency position. So, what we do? We always say that the fastest, slowest guy will determine the length of the time step. So, in this case, let us say it is 40 nanoseconds, okay, and so everything will be 40 nanoseconds, and this will be also 40 nanoseconds. So, this may be between 25 or something like this. So, in our case, what we have seen, so our T1 slow, so we have already seen that the frequency of T2 fast, that is also less than frequency of T1 slow. Why this happens? Because you can assume that this is the fast adder, you just assume that this is the first adder, these are slow adders. Okay. So, still the frequency of your frequency of your slow adders will be higher than your fast multiplier. So, in other words, the time period or time required to solve the problem will be lower in case of the slow adders compared to the time period required for the even the fast adders. Okay. So, generally what happens, multipliers are always very slow. Even if you take a very fast multiplier, it will be slower than the even the fastest adder. So, let us assume that we take everything very fast. Okay. So, let us take everything very fast. So, what we will do, you take T1 fast, here also you take T1 fast, here also you take T1 fast, and also here also you take T2 fast, because your job may be that I want to do everything very fast, very quickly. Okay. So, let us assume that it will this T2 fast will take say 40 nanoseconds to do the operation, and so T2 fast is going to take 40 nanoseconds to do the operation. So, this one is actually 40 nanoseconds. Okay. Now, what you say that? You say that we are using fast adders over here. So, instead of 25 nanoseconds for the slow adder kind of, let us assume that they do your job in 20 nanoseconds. Okay. So, now you are in a big loss. Why you are in a big loss? Because this even if I am using the fastest multiplier, still what happens, the time period taken is 40 nanoseconds. Okay. And if I am putting a very fast adder also, my time taken is 20 nanoseconds, but I cannot make this one as 20 nanoseconds, because then there will be a problem. So, by default this is 40, so this will be 40 as well as this will be 40. Okay. So, even by using a slow adder, by using a fast adder, I am not getting any gain. I am getting the result in 20 nanoseconds because they are using a fast adder, but still I have to wait for 40 nanoseconds, because everything is decided by the slowest guy in all the operations. So, that is T2 or operation 04. So, that is actually the slowest one. It is taking 40 nanoseconds. Even with the fastest guy I am having for type 2, it is 40 nanoseconds. So, all the time steps are 40 nanoseconds. So, so there is no use of putting a very fast adder over here, because the fast adder area will be higher than a slow adder, and time period may be also the case, and even the area and power of the slow adder will be less than the fast adder. So, here I am putting very fast adder, so I am putting more area and more power, and I am computing everything 20 nanoseconds, but still I have to wait for another 20 nanoseconds, because the time period is 40 nanoseconds and it is determined by the fastest element, slowest element of the block, which is at the multiplier. So, I am putting the fastest multiplier available, which is 40. That means I cannot have compute multiplication more in less than 40 nanoseconds. So, I cannot bring down the time step less than 40 nanoseconds. So, there is no use of putting anything very fast adder over here, because even if I am putting a fast adder, I am getting the solution in 20 nanoseconds, still I have to wait for 40 nanoseconds. So, let me try the other way. So, what I do is that this is 42 fast I am using, that I have to do, but now I am putting say T1 slow and also T1 slow. Okay, and here also T1 slow. So, I will get the answer in 25 nanoseconds, here also I will get the answer in 25 nanoseconds. But still I have to wait for another 40 nanoseconds. So, even if I get the result in 20 nanoseconds, even if I get the answer in 25 nanoseconds, it does not make any difference for the adders, because time step is 40 nanoseconds, so I have to wait. So, in this case, because this 40 nanosecond is determined by the fastest multiplier I have, I cannot go down between this. So, why I should use a 20 nanosecond fast adder, because fast adder will always take more area and power than a slow adder, and if I am putting a slow adder, I am not losing anything, because even if I compute the addition in 20 nanoseconds, or even if I do it in 10 nanoseconds, but I cannot get the answer earlier, because I have to have my time step of 40 nanoseconds because of the multiplier. So, what I will do is that typical intelligent designer will put a 40 nanoseconds multiplier is the fastest is available, he will put it here, and here he will not put a very fast adder, he will put a very slow adder, because he is getting the answer in 25 nanoseconds, and still I mean it is much less than 40 nanoseconds. So, anything below 40 nanoseconds is okay. Even if I have a very slow adder which will do my answer in say 30 nanoseconds, I will be prone to put that, because I want to do I do not want to increase, I cannot, the time steps are fixed to 40, and I will then within my motivation will be that I want to compute all my answers or addition answers in less than 40 nanoseconds, or at least equal to 40 nanoseconds, and I will be using as slow or as little hardware as possible. So, that is, we will take a slow adder, because slow adder will take very less area and it will take very less power. So, what I will do, I will use slow adders over here and I will use a fast multiplier over here. So, that is actually called the binding allocation problem. So, what I am doing, so what I am understanding, so what I am doing, I am finding out that this is the slowest guy. So, I will multiply the slowest part. So, even if I do my best effort, so even if I am using 2s type 2 fast, still this is actually say 40 nanoseconds kind of a thing, I cannot bring it below that. Then I will try to take the stuff, or so I will take such type of adders which will do my answer, it will get me my answer in less than 40 nanoseconds and take the minimum amount of power and area. So, I obviously use T1 slow and T1 slow and T1 slow over here, because they are going to give me the answer in say 25 nanoseconds, still which is less than 40 nanoseconds, and my area and power is less than using a fast adder. So, that is what is the motivation over here. So, it is written over this case. Okay. So, this is what I have written. So, in this actually I have given you some examples of frequency and time periods. Okay, I have saying 25 seconds as the time periods, 40 nanoseconds as the time periods. So, here in this slide is written in a general formula, like here is saying that the time period each control step is ft2 slow. Okay. So, I mean just you can go through this. So, I mean it is saying that the time period of each control step is T1 1 by T2f, that is the frequency of the fastest multiplier. Okay, so, but now you can think that if I am taking a very slow multiplier, then you will be in another very big problem, because now the time period of the slow multiplier may be say 50 nanoseconds, then the time periods of each of the time steps will be 50 nanoseconds now. So, I will not be prone to take a slow multiplier, I will be taking a fastest multiplier and a slow adder, because the multiplier is actually determining all the time steps, because it is the slowest element in the whole schedule operations. So, if you have another block which is doing a very complex operation, say which is mod computation, sorry factorial computation and all. So, then I have to concentrate on that, I will take the fastest mod computer, and then that will actually determine my time steps, and based on the requirement I will take such elements which will be the slowest in nature, but still do not overshoot the time step requirement. Like in my case of this multiplier, the multiplier was the slowest element, so I have taken a very fast multiplier which is 40 nanoseconds, then I will take adders slowest as slow as adders as possible, or as slow other elements as possible that do not overshoot the time requirements of 40 nanoseconds. So, it is saying that nobody, we have to find out the slowest element of the whole lot that is in set O, and that is, I mean that is actually set T or rather. So, you have to find out the slowest element in set T, that is the type of operators, and then you have to take the fastest version available for that, then it determines the time step length, and accordingly you have to use very slow elements of the other guys. Still you have to think that you should not overshoot the time step, that one. So, that is what has been written in the slide, I mean you can read through that. So, then actually this is, now we are coming to the third step. So, third step is the, I mean a bit complex step, I should not call it complex, but what happens here. So, in this case what we do, is now we have your scheduled operations, now we have binded elements. Binded elements means now all the scheduled operations has been allocated to some specific hardware, like hardware fast adder, slow multiplier, etc. kind of a thing. So, now what you have to do? So, in case of binding what happens? So, now you have to say that, like for example you might have said that we are using, like if you take this time control step, like if you take this example, that is better to explain here. So, in this case you see that we have used only one adder and one multiplier. So, you can think that this one will be T1 slow, this one is also T1 slow, this one is T1 slow, and this one is T1 fast. Now, this is your actually scheduled and this one is actually binded, everything is done. Sorry, allocated. Scheduling is this one and these are the allocations. Now, you have to bind it. That means what? You have only one adder. So, there is only one adder which is of type T1s, and you have to say that A and B will be first done with this one. Then again this temporary variable 1, temp 1 and temp C will be again done by the same adder, will be reused of the adder. Then you can say that again temp 2 and D will be again, I mean binded the same adder for a third time, which is being reused, and then you can say that temp 3 and E has been allocated, schedule allocated and binded. So, you can say that temp 3 and E has been binded to when this adder number 4, that is T1f. So, in other words what I am saying is that in case of binding, what I am doing, as we are reusing the elements, as you have seen in the example, as we are clearly always reusing the elements like adder, multipliers, we are reusing. Many times we do not use parallelism. Even if you are using parallelism, like even if you are using two adders in step 1, still one of the adders will be reused in the third step, as you have already seen. So, that is actually called the reusing. So, that means what? That means same variables or same operations will be binded to same hardware. Like first it will be A plus B, then it will be C plus D and so forth. So, actually binding actually the problem is that one. It says that which hardware elements binds to which of the operations. So, that is the idea. So, here it says that in the unconstrained time schedule, first example O1 and O3, O2 and O3. So, there is actually two hardwares are available. So, in one actually we do O1, the other we do O2, okay, and then in the second time step we do O3. So, you can take, say it is say adder 1, you do O1 and O2, or you can say that adder 2 I do O2 and O3. So, O3 can be binded to either A1 or A2, they are the two adders. So, that is actually then also you have to think about the variables like A, B, C, D, E were the input variables and they are the temporary variables. So, they has also to be binded to some kind of registers. So, that is particular operations or particular variables, then they are actually binded to or on which hardware or on which allocated hardware they have to do the operation is actually called the binding. Okay, so, we will explain with examples, then it will be more clear. Then actually we have three type of bindings, let us just define the type. Storage binding. So, storage binding means if it is input variables A, B, C, D, E, F, temp 1, temp 2, temp 3. So, which are the registers which they will be used to store. So, this is actually called the storage binding. Functional unit binding is very simple, like operation O1, which adder which has been allocated, which allocated adder they will be operated on, or which allocated multiplier will be multiplying a particular operation, and actually called the functional unit binding. That is which hardware will do which operation, and similar interconnect binding is the actually using of multiplexers and wires. Okay. So, that is about actually three types of binding. So, that we will all illustrate by an example which you are already using. So, actually already said that there are the three different binding steps which are like this one, the storage, function unit and interconnection binding, but they are three different steps although written in all texts, but actually they are all intertwined and they are done hand in hand. So, now we will illustrate the binding operation for the unconstrained schedule when the allocation is two types of modules, that is slow adder and fast multiplier. Already we have considered this, and O1 and O2, O2 and O3, they are your, this is O3, this one is your addition operation and O4 is the multiplication operation, and we are taking the case where it is totally unconstrained schedule, that is this is your two adders, that is O1, O2, then you add temp 1, temp 2, that is O3, and finally in the last step we have this multiplier operation which is actually O4. This is your unconstrained operation. So, two adders are in parallel in the first step. So, you require two adders, the same adder can be reused, and obviously there is one multiplier block. So, that has to be done to this one for the multiplication O4. So, let us look at, this is the basic architecture of the binding element. So, what we have? We have one register, one adder as you can see over here, there is another adder 2 as you can see over here, then A is one input, okay, then B is one input, C is one input and D is one input. Okay. So, now we have to say that A plus B, that is one operation, and C plus D is another operation. So, we allocate A plus B to adder 1, we bind A plus B to adder 1 and C plus D to adder 2. So, what will happen? A has to go to adder 1, B has to go to adder 2 in one step, simultaneously C has to go to adder 2 and D has to go to adder 2. That is what is being done. So, then some result will be generated which is nothing but your temp 1. So, temp 1 and plus temp 2 we are saying that we will again bind it to adder 1. So, this temp 1 from adder 1 will be fed back to this same adder, and the output of temp 2, that is actually the output of adder 2, will be again also fed back to your adder 1, because we have binded temp 1 plus temp 2 to adder 1. Now, what happens? The output is temp 3. So, it is generated, and this E, that is actually temp 3 plus E is actually A plus B plus, temp 3 is A plus B plus C plus D, that is actually multiplied with E. So, temp 3 star E is actually binded to multiplier. That is obvious because there is only one multiplication operation and one block is there. Now, what we will see that there are different operations. Now we will see how this happens. That is, in first step you add A plus B, then you add C plus D simultaneously, then you go for temp 1 plus temp 2, and then actually you go for temp 3 star temp 3. So, there are some time steps involved. So, let us look at how the hardware works like that and how actually the binding is happening. Okay, so, this was a very basic block level diagram. So, now we will see step by step. So, in control step 1, what happens? You actually have 4 active variables A, B, C, D, because in the first time step you are adding A plus B and C plus D. Okay, in time step 2, we have 2 active variables temp 1 plus temp 2, because you are adding in time step 2 temp 1 plus temp 2. In time step 3, what happens? You have 2 active variables temp 3 and A, because temp 3 is A plus B plus C plus D. And if you remember, the example we are taking is A plus B plus C plus D, and we are actually starting with E. This is our expression which we are doing. Okay, so now you see so we have to store this variable. So, we have seen that there are 3 types of, what do you call this variable? 3 type of bindings are there. So, storage element binding, let us say. So, we have 4 elements A, B, C, D. So, we have to give some registers where they can be stored. Now, you can see in time step 1 A, B, C, D, all of them are active. So, here actually you cannot save any kind of this thing. So, in time step 1 you cannot share any kind of a hardware, like for A plus B plus C plus D, all the A, B, C, D are all alive at time step 1. So, as all of them are in time step alive in time step 1, so obviously you require 4 registers for this one. So, 1, 2, 3, 4. So, 4 registers are mandatory, because in time step 1, all the 4 what do you call these 4 variables are simultaneously need to be stored. So, 4 registers has to be assigned, and that is actually you have to allocate 4 registers, and A is binded to register 1, you can say B is binded to register 2, C is binded to register 3 and 4 is binded to register 4 kind of things. You see A, then B, then C and then D. Okay, so all of them are binded to 1, 2, 3 and 4. But now you see in the second life cycle, second life stage, after A plus B plus C plus D happens, so this will generate temp 1 and this will generate temp 2. Okay, so now you can see the temp 1 and temp 2 do not share any kind of a common lifetime with A, B, C, D. So whatever 4 registers we have taken, or we have allocated 4 registers and binded with A, B, C, D, they can be reused to store temp 1 and temp 2. So that actually we can do over here. So you see A is actually in time step 1, what happens? Time step 1, this is actually at control time step 1. So this multiplexer actually sends A over here, B over here, then C is allocated directly to, binded directly to register 3 and D is going to register 4. So we are using 2 multiplexers because as I already told you, adder 1 will do A plus B and then it will be do temp 1 plus temp 2. So there is a multiplexer over here. So in time step 1, control step 1, you make the multiplexer control to be 0. You can see that we have made control this one equal to 0. So what happens? So this guy is flowing over here, this is already shown in the slide. So this guy is flowing over here, B is flowing over here, C is flowing over here and D is flowing over here. So you get temp 1 and temp 2 as the output. Now what happens in control time step 2? In control time step 2, if you see, we are making actually control as equal to 1. So in this case what happened? Your temp 1 should go here, temp 2 should go here and you are generating temp 3. In this case we do not require, because in time step 2 we are not at all requiring this adder. Okay. So now you see what happens. So this register is actually being shared by A in the first time step, temp 1 in second time step. Register 2 is shared by B in the first time step and temp 2 in the second time step. Register 3 is only storing 3, register 3 is only storing C, not to bother, and we will see that register 4 is storing D in the first time step. So it is binded to D in the first time step, but in the third time step when you are going for the multiplication operation, then what we have already done temp 3 plus temp 2 plus temp 3 plus temp 2 already we have added here, and we have got the result in this one temp 3, and then actually we have to multiply it with E. So now this will come via this register. Okay, so it will become via this register number 4. So register number 4 was storing a D in the first step, and in the third step it is actually storing the value of E, which so that it can be multiplied with temp 3. So register 4 is actually storing the value of D as well as T in 2 different time steps. So in other words, so we are using 4 registers here. That is what is being told in this slide. So we are using 4 registers. If you can see, we are storing 4 registers R1, R2, R3 and R4, and in the binding A and temp 1 is binded to register register 1, B and temp 2 is binded to register R2, C is binded to register 3 and D and E are binded to register R4. Okay. So that is actually your what do you say, what do I say, this is actually storage binding kind of a thing. Now we have some addition operations. So already told that O1 is done over here, O2 is done over here. This is A plus B and C plus D, it is control time step 2. Now at control time step, it is in control time step 1, O1 is binded here and O2 is binded over here, that is A plus B and C plus D. Now in this case you see in time step 2 this is not doing anything, this do not care, and here what we are doing, we are doing temp 1 plus temp 2, that is O3. So O3 is actually binded, you can say, to adder 1, and finally in the third step what we are doing, we are actually multiplying temp 3 with E. So O4 is actually binded to multiplier in the time step 3. So this actually is the story of binding in a nutshell, that is we are given 2 adders and 1 multiplier and we are required 4 registers. Okay, and so you have to bind A, B, C, D, E. A, B, C, D, E, they are the 4 input variables, so you have to bind them to different registers, exact register which will be storing the value at what time step, and also the 4 operations we have O1, O2, O3 and O4, you have to bind them to register adder 1, adder 2 and adder 4. So this is basically the idea of binding, we will explain with an example. Now what is interconnect binding over here? They are nothing but the multiplexers we have kept and the wirings. So you see in register 1 we are binding A and temp 3. So you require a multiplexer. So in one go A will go, and in the second time step in the second time step temp 2 will go, and in the third time step temp 3 will go. So actually in fact register 1 is being shared by 3 variables in this case, you should see. So in the first case, better to be more precise here. So in the first time step B is stored in register 2, okay, and A is being stored in register 1. So in the second time step temp 1 is stored in register 1, because this is the result of A1 plus A2. Then again what you do, again you add here you are again adding what? You are adding temp 1 plus temp 2. So temp 3 will be generated and it will also be stored in register R1. So basically register R1 is actually binding 3 variables, A plus A, then it is binding temp 1, and then finally it is also binding temp 3. So, this is actually A for first time step, A plus B, that is temp 1 is second time step, and the third time step, first is actually initial storage is A, then first time step you are computing temp 1, that is A1 plus A2, that is also stored in register 1, and finally in time step 2 you are calculating temp 3, which is also stored in register 1. Okay, so register 1 is actually can be shared by 3 variables, register 2 is shared by 2 variables, B and temp 2. So, in first step, the initial step you are reading the value of B, so that is stored in register 2, and temp 2 is binded to register 2 at the end of first time step. So, here actually we have B and temp 2, and in register 3 only C is there. So, only C is binded to register 3, and in case of register 4 D at the initial time step you read, and E also is read at the initial time step, but you are requiring E in the third time step for doing the multiplication. So, in the register 4 is binded to E at the third time step. So, now you require multiplexers. Why do you require multiplexers? Because if in first go register 1 should add load A, in the second time step it should add temp 1, in the third time step, second time step it should add temp 2 and so forth. In initial temp 1, then temp 2, then temp 3, all are actually loaded to register 1. So, obviously you require a multiplexer. So, there are some multiplexers over here you have to add, and they will actually comprise your your interconnect binding. Okay, so that is in a nutshell what we have seen. This is, if you look at this is your binding result. So, we say that at time step 1 O1 is binded to adder 1 and O2 is binded to adder 2. This is actually functional unit binding. O3 of adder 1 functional unit binding will be done in adder 1 or adder 2, whatever you want to say, that will be actually the second time step. Then we say that A, temp 1 and temp 3 is binded to register 1, already we have told you. B and temp 2 is done to register 2. Okay? So, this is actually storage binding. C is to register 3 and D and E are to register 4, binded to register 4. These are storage unit binding and these are actually functional unit binding. Okay. So, O3 actually in this case we are doing in adder 1. So, sorry for the mistake, is actually adder 1, O1 in adder 1, O2 in adder 2, this is in the first time step, and in the second time step O3, that is temp 1 plus temp 2 is again done in adder 1, and then actually O4 is done to multiplier 1, that is only there was obviously one choice. So, this actually completes your binding arrangement. So, given in this case adder, all the adders are you should know that they were actually T1 slow, okay, and it was actually T2 fast for the multiplier. So, this is what these are operations are. Physically they will be done by this hardware. So, if you define them, they will actually tell your binding step. Okay. So, with this we actually complete the the binding procedure of your high level synthesis process. Now, what we have done, one small step is remaining, that we will see. So, what we have seen that there are some multiplexers over here. So, in the first step of the multiplexing, so what we happen, we make control 1 equal to 0. So, that means what, A is flowing over here, B is flowing over here, C is there, and obviously D is flowing over here. In the second time step what we have done, so we require that temp 1 should go over here, temp 2 should go over here. So, we made control 1 so that the multiplexer, the second bit is selected. Okay. So, in the second step we made control 1 equal to 1. The other multiplexer and this adder is not required, so do not care, we do not require this. And again in the third time step what we have done, so again we have kept it 1, so that temp 3 generated kind of a thing, and here actually we require control 2 to be 1 because E should flow over here. So, these are some of the control signals we have to generate. So, what happens here? So, you require in step 1 control 1 is 0, control 2 is 0, in time step 2 control 1 is 1, control 2 is x because second adder is not required, and in third step control 1 is 1 and control 2 is generated. So, you now have to generate a sequence with values 0 0, 1 x and 1 1 in 3 consecutive clock cycles. So, that can be very easily generated by a finite state machine, like with output state 0 0, state 0 1 and state 1 1 you can say, and these are moving back. So, if you can at each clock pulse you will move around this finite state machine. So, initially 0 0 and sorry, it should be not 0 1, it is 1 0 you can take, because the second bit is do not care over here and third bit is 1 1. So, if you go around this finite state machine at each clock step, so you will be able to generate this control path. So, after doing this scheduling, then we have done allocation and then we have done the binding. That is, we have allocated A, B, C, D to different registers, then temp 1, temp 2, temp 3 to different registers, and actually multiplexing arrangements we have done, and also we have said that operation O1, O2, O3 to different adders and O4 to a multiplier. So, after completing this what you can call this binding procedure, then we have found out the control signals. There should be 0 0, 1 x and 1 1. So, that can be very easily generated by this finite state machine, right? And so, this can be very easily synthesized using digital circuit fundamentals, and that will complete your whole RTL design, that is your high level block diagram. So, this is your high level block diagram finally, and this there will be another block level diagram which will generate the control sequence. So, here we will have this finite state machine which you have already drawn. So, this is the output of the high level synthesis procedure. So, what we have started with, we have started with a example, that is with a specification, that is A plus B plus C plus D star E, and then finally at the output we should get this architecture, that is a block level architecture, and then which is where the operations are scheduled, allocated and binded, as well as this control structure. So, after that we go for the gate level synthesis, which is the next step of the design flow. Okay. So, now in the next lecture what we will be looking at, in the next lecture we will be mainly looking at how we can have automated algorithms or automatic procedures where given a specification like A plus B plus C plus D star E and some design constraints like unconstrained design, resource constraint, time constraint, automatically you will get a schedule, allocated and binded design ready. So, that we will be looking at in the next few lectures. Okay. So, before we stop, there is a question answer session. So, among all the 3 steps of high level synthesis already seen, scheduling, allocation, binding, what cannot be done, what can be done without information regarding the design library. Like we are saying that, I mean, design library means whatever hardware is available to you. Okay. So, that only those things that can be used in the design, like you cannot have a 10 input AND gate. For if you have a very good design library, then you can have different type of adders, but if you have a very rudimentary design library, then you may have only carry look, triple carry adder and so forth. So, based on the design library, which what can be done in the 3 steps, what can be done without any information of the design library, or which of them is steps are independent of design library information. So, already we have decided seen that scheduling and binding, they will do, they will actually in the scheduling we give different time steps to different operations, and in binding what we do, we have different hardware modules where we physically bind which operations to be done in what. So, these 2 are basically bit general steps, but in allocation what we do, in allocation we actually look at the design library and then we see what are the time steps. Already we have seen that we have used a very fast multiplier, but we have used slow adders based on the timing requirements of the multipliers and the adders, and based on that time step we have already decided that it is very good to use a single we say that it is good to use a fast adder, a slow adder and a fast multiplier. So, this allocation stage, looking at the frequency, power requirements and all. So, allocation step, it is very important to have a idea about what is in the design library. So, without having an idea about the design library, you cannot go for the allocation step. But the other 2 steps like scheduling and binding, so I mean very strictly speaking, scheduling, you do not require any information about the design library. It is a generalized step and you are assigning operations to different time units. But allocation, it is mandatory to know that design library information is there. Based on that, you select which exact hardware you are going to use. And even if you do not say you have bypassed the allocation step because you do not have that information. So, even you can say that I use adder 1, I use adder 2 type, adder 3 type, multiplier type 1, but exact details you do not know because you do not have the library information. Still you can go about the binding step, because in this case you have to physically bind the operations to different hardware. But without the design library information, allocation step cannot be done. So, with this we stop here, and in the next lecture we are going to see automated procedure for going about high level synthesis, the first step, that is scheduling. So, next lecture we will see scheduling procedures, automated scheduling procedures, that is what. Okay, thank you for this.